Hello viewers, I am very happy to meet you all today. All of us would have seen these gemstones. They are used to make jewelry. These gemstones are naturally occurring minerals in the form of rocks or organic materials. We can collect them, cut them, polish them and use them to embed in the jewelries. There are two types of gemstones, precious stones and semi-precious stones. We know the examples for the precious stones: diamond, ruby, emerald, sapphires, etc. For semi-precious stones, topaz, turquoise and garnets, etc. From these gemstones, today I am going to pick up the ruby crystal, the ruby gemstone, and I am going to share how these ruby crystals can be used in the development of ruby laser. Ruby laser, let us discuss today. I am Dr. G. Littlefla, the faculty from the Department of Physics, Stella College, Vijayawada, Andhra Pradesh. Historically, these ruby crystals stand as symbols of power, passion and protection and are considered as king of gemstones. They occur naturally or man-made synthetic way also they are available. Natural rubies are very rare and expensive. Synthetic rubies are widely used due to their lower cost and unique optical properties. Ruby crystals have good hardness, scoring 9 on the Mohs scale of mineral hardness, making it second to diamond in terms of natural minerals. Thus, the ruby crystal is very significant not only in jewelry preparations but also in science and technology, particularly in the development of laser technology. Theodore Maiman was the first man to prepare ruby laser out of this ruby crystal in the year 1960. Let us now discuss nature of ruby crystal. As such, ruby crystal is composed of aluminum oxide. Chemically, the chemical formula is Al2O3. So, with aluminum oxide alone, ruby crystal appears colorless. But a small percentage of chromium oxide, chemical formula is Cr2O3, when they are added as impurity atoms to the ruby crystal when they are grown in a special furnace, then the ruby crystal gets some beautiful color. These chromium Cr3 plus ions act as impurity atoms typically at 0.5% to 1% in the ruby crystal and replace some of the aluminum ions in the crystal lattice. They absorb the green and blue light of the natural light. That means natural light has 7 colors, but these chromium ions absorb green and blue part of the natural light, giving ruby crystal a beautiful deep pink hue. The main components of the laser we know, we need a active medium, we need a energy source and we need a resonator, optical resonator. So here in ruby laser, the active medium is going to be chromium ions, Cr3 plus ions. The ruby rod will just act as a host material only. And as energy source, we are going to use a helical xenon flash tube which has a power supply source. When we put it on, it provides a pumping light which raises the chromium ions from the ground state to the excited state. Xenon flash will appear like a white flash with bluish, slight bluish tint. The flash of xenon tube lasts several milliseconds only, just very fraction of second, and the tube consumes several thousands joules of energy. Out of this huge energy, only a little part is going to be used in pumping Cr3 plus ions from the ground state to the excited state. The rest is going to heat the apparatus. So to protect the apparatus, we need to arrange a cooling arrangement. And next is the optical resonator. Here you can see the optical resonator. So the left side and the right side of the ruby crystal, the pink color is the ruby rod. Both sides will be well polished and made parallel, and then silver coating will be given here and make this side of the ruby crystal fully reflecting mirror, and the right side we have partially reflecting mirror. So when the xenon flash tube is on, the light flash will excite the chromium ions embedded in the ruby crystal as impurity atoms will be excited to the higher energy level, and when they return, then you see that those photons will be emitted, which is called laser output pulses. The next, the actual picture is shown here. You can see the ruby rod here. It is surrounded by the xenon flash lamp. This xenon flash lamp has a power source and there is a switch, and then you have a 95% reflective mirror this side and 100% reflective mirror this side, and the ruby rod pink in color is inserted, and the xenon flash lamp as a spiral, it is surrounding the ruby crystal. This is a picture. You could see that when the lamp is on, it just sends out a flash for a milliseconds only, but huge energy is utilized, and the most part of the flash energy will go in heating the apparatus. So we need to provide the water cooling. So there is an inlet and there is an outlet through which water is circulated so that the apparatus can be cooled. Next, we will see the energy level diagram. Before going to the energy level diagram discussion, let us revise the fundamental formula. From Planck's law, we know E equal to h nu. H is Planck's constant. Nu is the frequency of the light photon. We know velocity of light, c is equal to nu into lambda. Nu is the frequency of the light, lambda is the wavelength of the light wave. So from this formula, if you find what is nu, which is equal to c by lambda, substituting that in the equation 1, we get E equal to hc by lambda. So from this formula, we can say that E is inversely proportional to the wavelength. Now, the energy level diagram of ruby laser is having 3 levels. One is E0, another is E1, and the other is E2. This E0 is the ground state, and this is the excited state. This is the excited state, and this level E1 is called metastable state. E1 is called metastable state. Now, we send a flashlight of wavelength 550 nanometer. So when we switch on, the xenon flash lamp will send a flash for milliseconds with wavelength 550 nanometer. So this photon will excite the chromium ions which are in the ground state to the excited state. So this is what called optical pumping or optical transition. So chromium ions, Cr3 plus ions, get transferred from the ground state to this excited state, where the lifespan of the chromium ions in this state is 10 power minus 8 seconds. So when that time gets over, chromium ions lose certain part of energy to the apparatus and they jump back to the level E1, which is called metastable state. This time there is no radiation, there is no emission of photons. So we call this transition from the excited state to the metastable state as radiationless transition. Now in the metastable state, chromium ions have lifetime 10 power minus 3 seconds, definitely longer than the 10 power minus 8 seconds. Now, when the chromium 3 plus ions in the metastable, one of them, when they jump back to the ground state, it emits a photon. It emits a photon. This is by spontaneous transition. So, when they stay in the metastable state, some of the chromium ions jump back to the ground level by spontaneous transition, and they emits a photon. This photon will go and interact with the chromium ions staying in the metastable state. Now each chromium ion absorbs this photon. Now what happens? That cannot hold that much energy, so it gives off its energy as a photon as well as the absorbed photon. So these emitted photons now will be interacting with the other chromium ions in the metastable state, and you can see many photons are coming out. They are traveling in the same direction, having monochronicity and coherence, highly directional and highly intensive also. Now these photons, so let us see now working of the ruby laser. Already I told all these things. E0, E1, E2 represents the energy levels of the chromium ion. So when the xenon flash of 550 nanometers strike the chromium ions in the ground state, they get excited. They go to the excited state E2, where they spend time 10 power minus 8 seconds. Through radiationless transition, they jump to the metastable state where the lifetime is 10 power minus 3 seconds. Now from the metastable state, the chromium ion jumps from E1 state to the E0 state by emitting a photon. These photons will interact with the excited chromium 3 plus ions in the metastable state and stimulate them to come to the ground state E0 by emitting photons. Now these photons in the resonator will be reflected back and forth. So when these photons in the resonator move forward, backward, they gain more energy and their strength gets amplified. At one point of time, when enough energy is built up, the light escapes through the partially reflecting mirror and come out as a photon with a wavelength 694.3 nanometer. Now when the previous diagram we'll just see. Yeah, you can see when all the chromium ions jump back to the ground state, the lasing action stops. Now if you want that ruby laser to give another pulse of laser, then you have to put on the xenon flash once again. So this way, continuously whenever we need laser pulses, you have to put on the xenon flash tube and get the flash and activate the chromium ions from the ground state to the excited state, and we get laser pulses through stimulated emission. Now, what are the drawbacks of the ruby laser? The ruby laser has lower efficiency. The xenon flash, to glow, it consumes many thousands of joules of energy, but only very little part is used in activating the chromium ions from the ground state to the excited state and make them to come to the metastable state, and we get the laser light. So low efficient. Most of the energy just goes to heat up the apparatus only. And with all the struggle we get laser output, but they are only pulses and not continuous laser beam. So this is another drawback. And whenever you use a xenon lamp, you need to use cooling requirement. Then they have limited wavelength, only one particular wavelength, 694.3 nanometer alone is coming out. Whereas for applications we need lasers with higher wavelengths, many wavelengths. So this gives out laser pulse with single wavelength only, and the alignment will be very, very difficult. Okay, setting up the cooling arrangements, anode lamp, it is not very user friendly, and the ruby crystals have very limited lifespan. If you use it for creating high intensity laser applications and then they get spoiled, you have to replace the ruby crystal. Applications of ruby laser, they are used in holography to create beautiful holographic images, and for tattoo removal and the wrinkles on the face, we can use the ruby laser. This ruby laser is also used in range finding like LIDAR, light detection and ranging. So for communicating between the spacecrafts and all, we can use this ruby laser also. And other applications include in a thin crystal of small area, these ruby lasers are used to drill small holes so that they can be used in the ornaments. And in microscopy, this laser light helps us to study and analyze the tissues, behavior and their nature. Biological samples can be studied well. Ruby lasers are used in laboratory experiments. It is used in soldering and welding. It is used to test the quality of materials. It is also used in the treatment of detached retina and so many other applications. So with these applications, let me wind up today's topic. I hope you all have enjoyed this discussion and know something about the ruby laser and its functioning. Thank you all.